Hello.
Shall we start, sir?
Hello.
Hello, Nagaraj sir.
Pradeep.
Yes, sir. Shall we start, sir?
Pradeep, can you hear me?
Yes, sir. Yes, sir. You are audible, sir.
Yes, please. Okay. Okay. Anuraj, you can start.
Okay, sir. Okay. Good afternoon, all. I welcome you all for the fifth RAC of my research scholar, Anuraj. Now I request Anuraj to start his presentation.
Thank you, sir. Sir, am I audible?
Yeah. You're right.
Sir, slides are visible, sir.
Yes, it's visible.
It's
Visible. No problem.
Thank you, sir. Good afternoon, one and all. Myself, Anuraj, research scholar from the Department of Mathematics under the guidance of Pradeep Kumar, sir. Like my thesis title was, we framed like a way like analysis of flow stability and dual solution of Newtonian and non-Newtonian fluids over a curved surface. This is our thesis title, and now this is the overview of my section. Like I am going to give some objective. I mentioned my objectives and introduction, literature review, and design and framework of my model, governing equations of my model, and stability analysis and conclusion. These are the objectives of my thesis. Like among five, two are completed. This is the third objective, like analysis of stability and multiple solution of heat transfer of non-Newtonian fluid over a curved surface. Based on my objective 3, I did a literature review for my objective 3 here. These are the major results I found from the literature review. From this, I included the things like tangent hyperbolic fluid and Lie group analysis. Like tangent hyperbolic fluid, still now there is no study was on curved surface. That's why I choose the non-Newtonian liquid tangent hyperbolic fluid, which is a shear thinning fluid. And Lie group analysis, like scaling similarity transformation, also still now for curved surface not studied. For the stretching sheet, they studied the Lie group analysis, but curved still now they didn't did according to my literature review. And based on my objective, I framed the title of the research article, like analysis of stability and dual solutions of tangent hyperbolic fluid over a nonlinear curved surface with nonlinear radiation influx. Here my aim is to find the dual solution of the problem. Like dual solutions are important because they reveal that variation in the mass transfer or suction parameters can lead to multiple mathematical flow states, embedding researchers to distinguish between the physical reasonable state and unstable mathematical solutions. Here, basically, I am getting two kinds of solutions, like physically reasonable stable solutions and mathematically unstable solutions. To different, this helps us, the researchers, to distinguish the physical region and mathematical solutions. And mainly for me, like I'm getting the dual solutions of velocity profile, temperature profile, and chemical concentration profile of the nonlinear over a flow over a nonlinear curved surface. And my scope, like to find the engineering quantities like skin friction, Nusselt number, and Sherwood number. And mainly this objective was focused on the nonlinear curved surface and tangent hyperbolic fluid and nonlinear radiation and chemical reaction, like a destructive chemical reaction I consider here. This is the major application of my model, like it is a production of polymer sheets kind of thing in the industry. Like this involves the 4 stages, like a process feed and a coating stage and shaping stage and curved shrinking stage. Like at the starting, we include the chemical compositions in the extruder, and the chemical compositions becomes a liquid in the process feed mixing, and it becomes a liquid form. Through dye it is flowing, and that by the cooling effect, that liquid becomes a solid state. By the nip roll, this becomes the sheet kind of thing, like by in the nip roll, by transferring that nip to the nip roll, it becomes a curved surface kind of thing. This is the which is the curved shrinking surface, like a kind of way. This is the application where we can see the curved surface. And I framed this design into the schematic representation with the curved surface, considering the capital R radius of curvature. And here S is the flow direction, and along the S direction velocity is U, along R is the horizontal vertical direction, and velocity along R direction is V. And I consider the horizontal magnetic field BM, and from the BM, I am getting the Hartmann number when after the non-dimensionalization, that is M. And here QR is the radiation parameter. Especially I am using here nonlinear radiation. For the nonlinear radiation, after non-dimensionalization, we are getting RD and theta W. And here majorly I am considering, I am introducing the suction parameter and shrinking parameter. Because of this only I am getting the dual solution. Why it is dual solution means, when we applied the suction, it pulls out the flow. When it pulls the flow, and for the shrinking also, the flow becomes inward. When it becomes inward, there will be bifurcation point. That's why it is a dual solution. And here I am using the no slip boundary condition. Like this is the no slip boundary condition. Delta 1 will be the no slip boundary slip boundary condition. Slip boundary condition. Here I am using the first order slip condition, and here I am using the convective and thermoconvective and solutal boundary conditions. What is the importance of that boundary conditions? Like what is the use of these boundary conditions? Means, like when we apply the slip boundary conditions, that becomes that free boundary to the rigid boundary. Because slip is happening on the surface, like it becomes a rigid surface. And here that convective boundary conditions, what happens means that isothermal to adiabatic condition, it becomes isothermal to adiabatic. Means isothermal means that T is equal to TW. When adiabatic means that dou T by dou R is introduced. That's why that there is no heat transfer between the outside and surrounding and in the liquid. That's why the convective boundary condition I am using here. And I'm also using the Darcy-Portsmouth model. That's why it is a porous medium is included here. This is my design framework of my schematic representation of my model. And here, basically for the shrinking, it involves the backward flow. We can see here, the backward flow in the figure D. We can see the backward flow, which leads the boundary layer separations and non-unique solution, which separate within the specific parameter. This is how the shrinking parameters works. Like it is an inward motion. After that, we can see here. We can see here that there is an inward motion here, and over a distance, it becomes and it decreases, and later also it increases. This bifurcates and it becomes a dual solution. Similarly, for the temperature profile also, we are getting this condition only holds for only shrinking and section parameter. It involves then only this condition, this boundary layer will arise. So for comparison, I showed here also for the stretching cases. For the stretching cases, only single boundary layer we are getting. We can see this one that at the boundary it is increasing. Later on, it also increases more, and later it decreases. This is the stretching case of the boundary layer for the velocity and temperature. And now I got to know that our solution, I'm getting the two solutions. That's why I differentiated methodology into two parts. Like one is for the boundary value problems, and one is the boundary eigenvalue problems. Because of the dual solutions, I also studied the stability analysis to tell which is the physically stable solution. For the first part, the equations, when we convert the PD to OD using the scalar similarity transformation, it becomes a boundary value problems. Using BUP5C code, I am going to solve those boundary value problems, coupled boundary value problems. And in the part 2, I am going to see I am introducing the eigenvalue and eigenfunctions, and this converts to the boundary eigenvalue problems, and that is I am going to solve using the BUP5C code. And these are the vector form of the governing equations. Majorly here I consider that tangent hyperbolic, the tau represents the tangent hyperbolic fluid, and this J cross B is the magnetic field term, and these two are the Darcy-Forssmiller terms. Here nonlinear radiation I am using here, that is a QR here, and J square is the Joule-Litting term. And here HR C minus C infinity is the destructive chemical reaction. When HR is greater than 0, it is a destructive. When HR is less than 0, it is a constructive chemical reaction. And DM is the diffusion of the mass transfer. And here the component forms of the governing equations I mentioned here. From the vector form, I reduce it to the component forms. Here all the shear stress parameters also mentioned here, as we can see here. And here also we can see that I only consider the magnetic field along R direction, and Lorentz force, Joule-Litting, and nonlinear radiation. Here I am neglecting the electric field, only magnetic field I am considering here. And these are the shear strums in all the directions, like RR, SR, and SS directions. But after applying the boundary layer approximation, my shear stress term will reduce it to only dou U by dou R minus U by R plus R. This all becomes 0 because your radius R plus R is the less value. R plus R whole square will be the more less value. That's why I am neglecting R plus R whole square terms. And I also only considering my flow is only along the U direction. That's why I also neglected the V terms. Now this is the reduced form of my governing equations. That is the first one is the continuity equation, momentum along R direction. Only these two terms will remaining when we after applying the boundary layer approximation. And for S direction, this is the governing equation. Similarly, for the temperature equation, this is the equation, and concentration also we can see this one. And here the boundary condition that S and lambda will be that small lambda is the stretching parameter. That capital lambda is the mean free path of the term, and this term will be non-dimensionalized into. It is non-dimensionalized only. That Kn will be nothing but the condensation number. It is for the slip parameter we are getting that one. This is convective boundary condition and soluble boundary condition. These are the boundary conditions, and after combining the independent terms one side and the dependent terms one side, and after applying the like group analysis, I am going to derive this. Using the scaling similarity transformation, I am going to derive the similarity variables. These are the new similarity variables for the Williamson hybrid Williamson fluid. Sorry, not Williamson, tangent hyperbolic fluid. We derived these equations. And it looks like this for nonlinear equations. When n is equal to 1, it becomes linear. We can cross check whether it is linear or not. And this is the stream function. When we see the stream function, it obviously satisfies the continuity equations, and remaining momentum equations. Two momentum equations are the 11 and 12, and 13 will be the temperature equation, and 14 will be the concentration equations. After solving 11 and 12, removing the pressure term, we are getting the fourth order ODE, which is like this. Where M is nothing but the power law index of the tangent hyperbolic fluid. W is nothing but the Wilber's number. These are the non-dimensional parameters I mentioned here, and I also mentioned here how it is non-dimensionalization. We can see here. Here W is the Williamson number, Fr is the Forssmiller number, phi is the porosity parameter, M is the Hartmann number, and CR is the chemical reaction rate constant, and gamma 1 is the slip parameter, These are the that Kn will be the condensate number. These are the non-dimensional parameters. After getting the boundary value problems, now my physical quantities will be the skin friction, Nusselt number, and Sherwood number. Majorly here, skin friction involves the tangent hyperbolic fluid. That's why here in the skin friction I included the tangent hyperbolic terms, and here Nusselt number radiation, nonlinear radiation is there. That's why here it is important. That's why I mentioned here. This is the major study of my research. That is the engineering quantities of the flow problem. And I used the BUP5C method for to solve the boundary value problem. This is the methodology, and after that I validated my BUP equations, differential equations with Raj et al, which was solved by the shooting method, and it is matching. And when kappa tends to infinity, actually kappa is nothing but 1 by r. When r tends to 0, that kappa becomes infinity. When kappa becomes infinity, it becomes a stretching sheet. For always, it is known that skin friction of the stretching sheet will be the 1. That is also satisfying here. That's why here I placed that lambda is equal to 1. That lambda is greater than 0 means it is a stretching case. Remaining n is equal to 1 is a linear stretching case. That's what here n is equal to 1. Theta w is equal to 1 means it is a linear radiation. But r is 0, then radiation becomes 0. After that, these are the major results here. Here dual solutions are very important. I said already that because it is able to find the two solutions. Now we can see one of the parameter like suction parameter. When suction parameter increases, actually physically what happens when suction parameter increases, that all fluid particles comes to the near the surface. When suction parameter is increasing means it pulls out the velocity, but initially it has a fluid particles which helps to fluid flow fastly. That is thing here. Like that's why when suction parameter increases, but the suction parameter is always negative in nature. Like suction parameter increases, that negative values increases, that flow is increasing. For the upper solution, we are getting the increasing velocity. For lower solution, we are seeing the decreasing. But now we don't know which one we should take. For that only, I am going to take stability analysis. Similarly, for shrinking parameter like lambda, this is we can easily observe and we can also predict this one. See in the physical state, when shrinking happens means the flow is inward. Inward means it is opposite to flow direction. Opposite to flow direction means that always flow will decreases. When shrinking parameters increases, the flow will decreases. But that's what we can see in the upper solution, it is decreasing. But in lower solution, starting it is increasing, later starting it is decreasing, later it is increasing. But physically it is not possible. But in by the seeing also we can tell that physically it is not possible. But in mathematically I am getting two kinds of solution. Now my challenge is to say which is the better one, which is the best solution. Similarly, like that I solved for the I'm showing here for that power law index of the tangent hyperbolic fluid. When power law of the tangent hyperbolic increases, actually what happens means when viscosity increases, flow should be decreases. But here I'm showing when viscosity when m increases, flow also increases. What is the difference here means like when m increases, we saw in the Gorley equation it is 1 minus m. 1 minus m means like 1 minus m means it is a less it is m increases means there m is decreasing. Means m is decreasing means viscosity is decreasing. When viscosity will decreases means obviously the velocity will increases. That is why velocity is increases when physically valid. For the upper physical valid region for the upper solution. Similarly, in lower solution also starting it is decreasing, later it is increasing. But physically lower solution is not valid. Similarly for the slip parameter, that also we can predict. Like for the slip parameter, what happens when slip parameter is increasing? It becomes to free to rigid boundaries. When free means the slip is happening there here. When slip is applying here, slip is happening and flow is increasing. It's obvious. That's why it is increasing here. Velocity is increasing. But in a lower solution, I am getting the decreasing also. mathematically I am getting this solution, but physically it is not valid. That one later we are going to do with stability. Similarly, for the suction with temperature parameter, we can see when suction parameter is increases, what happens initially liquid will come near to the surface. When when the fluid comes near to the surface, because of the warmness of the fluid, the temp in the surface of the in the sheet also the temperature flows very fastly. Like when temperature drop happens, drawing the fluid into the porous surface force, due to the warmth of the fluid close to the sheet, cooling the immediate region and lowering the overall temperature profile. That's what it is happening. Like when it is coming near to the surface, fluid that cooling it is happening. Similarly, when Prandtl number is increasing, like for higher Prandtl number, the temperature field will be decreases. And next year for the Biot number, when Biot number increases, actually that temperature profile is increasing, because when Biot number is increasing means it becomes isothermal to adiabatic. There is no heat exchanges when whatever we are giving the Biot number, that's why temperature increases. Like similarly for the radiation parameter, when external radiation is given means the temperature will always obviously increases. That's why it is increasing. Similarly for suction also, we are when higher the suction values increases, the convective transfer of mass towards the wall, making the convective boundary thinner. That's why it is decreasing here for suction. For this is chi is nothing. Xi is nothing but the soluble Biot number. When soluble Biot number increases, concentration also increases. And here I am also getting two solutions, like upper solution and lower solution. Both are increasing here. But there is a two nature of solution. Two nature only, but we should know which one we should take, that which profile we should take. Similarly, still now I discussed about the temperature, velocity and concentration profiles. Now physical quantities, when we come to physical quantities, like here we can see the skin friction, Nusselt number and Sherwood number. For the nonlinear stretching index, like N is the nonlinear stretching index. When N increases, for upper solution it is increasing, but in a lower solution first it is decreasing, later it is increasing. Means like here there is a critical threshold region also we are getting here, critical points also we are getting here. Like this is the bifurcation points, like it is a cutoff values. Like below this we'll get a dual solution, at that point we will get a unique solution, greater than that the solution won't exist, like that. Here also I'm getting the two solutions, and these are the critical points I found. And similarly for power law index also I showed here, same kind of thing it is happening. Next I did the stability analysis, because now I'm getting the two solutions. Now I don't know which one I should select. That's why over a time I consider the unsteady case. Over a time I introduced it here, and now I introduced the eigenvalues. Gamma is nothing but the eigenvalues, and F naught, theta naught and phi naught will be the eigenfunction. Capital F naught, theta naught, phi naught is the eigenfunction. And now that when I introduced the eigenvalue and eigenfunction, then the boundary value problem is reduced to boundary eigenvalue problems. Here using this convective and soluble and slip boundary condition, when I solved the boundary eigenvalue problem, now I am getting the eigenvalues like this. Initially you saw that I assumed the eigenvalue is negative. See, eigenvalue is negative when positive eigenvalue, but when I getting the positive eigenvalues, there is initial decay that doesn't affect the field. Then it is a physical stable region. But initial decay, later also decay happening, like initially decay that affects the physical situation, and it becomes the unstable region. And this is the critical suction number, that 1.25567. And this is the stretching case, like shrinking case I am considering, like lambda is equal to -1. This is the number, from this onwards only we are getting the two solutions. At that point only we are getting the unique solution. Before that we are getting the we are not getting the solutions. That's what the my analysis here. Basically, this is the conclusion. Whatever I said, it is in the same form in the conclusion. Basically, I want to conclude like this. This design accuracy this helps in design accuracy. Recognizing both branches prevents engineers from the designing industrial process like as polymer processing and wrapping shrinking sheet processes around the unstable lower region, which would lead to the sudden flow breakdowns. Like in some real world cases, sudden breakdown of the flow can happen when they consider the other cases. That is the main useful of this study. And thank you one and all. And these are the conferences and workshops I attended. And in this year, I attended two conference. And these are the paper presented in the conference. And one paper is published, and one more is in preparation of submission to the journal. And that also we are working. And these are the references I referred. Thank you. If you have any questions, you can ask.
In which journal it is published? Under?
Sir?
You have one publication, no? In which journal it is published?
It is in multi-scale and multidisciplinary modeling experiments and design, sir, which is Springer Publications. Now it is in Q3 journal. When I submitted, it is Q2, sir.
Good. Okay. And how many these conferences you attended in this period?
Sir, this year one online, both are online conferences I attended, sir.
Okay.
I presented my paper in both the conferences.
This is your fourth progress report or fifth one?
For progress, sir, I completed coursework, and this is my RAC 5 and APS, sir.
And about this one content.
Yes, sir.
Now, which fluid you considered?
Sir, tangent hyperbolic fluid, and with my literature review, there is no study in curved surface with tangent hyperbolic fluid, sir.
Okay. That Prandtl number, no? That what is the range of that one Prandtl number for the fluid you considered?
Sir, for water, it is 7, sir, like 7.
Up to 7 you can take.
For whole study, I considered for 7 is my Prandtl number. For the case to show the variation of the temperature profile, I considered 3, 4, and 5, sir.
So, okay. So how this curvature parameter affect your this dual solution?
Yes, sir. When curvature increases, velocity also increases, sir. That also I studied, sir. Okay. There also we'll get the two kinds of solutions, sir. But I didn't mention here.
Okay. So which one is stable you studied? Dual solutions you got, no? So which one is stable?
Majorly, my dual solution is coming from suction and shrinking parameters, sir.
Okay. So what type of surface you considered there?
What kind of surface? Like non-linear curved surface, sir.
Any particular wedge surface, cylindrical or something like?
Curved surface, sir.
Curved surface, okay.
Sure. Like I considered porous also, Darcy porous medium also, porous type curved surface, sir.
No, curved, they are different, you know. Porous, even in the flat plates, you can consider porous media. Okay.
Yes, sir.
This curved means what type of shape that curved surface? That's I wanted.
This here that I constant radiation radius of curvature I considered. This is the shape of the surface, sir. Like here we can see in the slide number 10 that curved surface. This shape I considered like this, sir. Like I am consider a curvy linear coordinate system, sir. Like R and S are the curvy linear coordinate systems.
What is the advantage of using curvilinear coordinate system over the Cartesian coordinate system?
Because of this curvature, because of the radius of curvature, now it becomes curved like surface. That Cartesian here, it is difficult to solve the equations, sir. Here for Cartesian, this parameter will excluded. When we applied Cartesian coordinate system, this parameter we can't able to mention in Cartesian, sir. That's why we took the curvilinear coordinate system.
Okay.
To consider the curvature parameter.
Okay. What is your this one next future plan?
Future plan, like I want to expand this to the entropy. Sir, I also saw that for entropy also we are getting the dual kind of solution. That one I need to show in next coming objective, and I'm planning to change the method, like any other neural methods I am planning to do, sir.
Neural method, can you explain?
Like physics informed neural network method, I want planning to implement for the curved surface.
Oh, is there the literature, in the literature it is available?
Sir, for physics informed neural network is applied to stretching sheet. Still now curved surface, only one paper is applied. That too recently it is published in scientific reports, sir.
Okay, good. Now we want to apply that method.
Yes, sir.
Okay. Good. All the best to you. Yeah. Nice.
Thank you, sir.
Thank you, sir.
Thank you, Pradeep.
Any other questions?
Another candidate
from audience?
Yes, sir. Yes. Along this direction. Entire surface is porous, ma'am. That's why in the boundary condition I am not including the porous term. Only in the momentum equation only I am including the porous term. This one. This one. Dual solution. Yeah, ma'am. Throughout I no stretching. Ma'am, stretching, when we consider stretching, it is unique solution. That is compulsory. Because of shrinking only, I am getting the dual solution. That's what here it is shrinking like this. Because of shrinking only, that dual solution is arising. That bifurcation point is arising. The stretching case, what for comparison purpose, that validation table I considered for stretching case. Yeah, ma'am. Yes, ma'am. Yes, ma'am. Yes, ma'am. Okay. Okay. For the understanding purpose, I mentioned, ma'am, that's okay. Okay, ma'am. Okay. Throughout my paper, I kept as PR as 7, but that also won't satisfy. That's water, but Newtonian, it is a not like, yeah, man, understood, man. Yes, ma'am. Okay, okay. Yes, ma'am. Yes, ma'am. Okay, okay. Yes, ma'am. Yeah, ma'am. Which parameter is dominated? Yeah, ma'am. Yeah, ma'am. That too, that is suction, ma'am. That is the major. This one I kept as 1.7, 1.8 as all the cases. Yes, ma'am, it is increasing. Yeah, ma'am. I also neglected this kind of things, ma'am. It is only mathematical kind of solution right now. That's why I am not considering about this solid line. Only dashed line I am considering. Yeah, ma'am. F prime. Yes, ma'am. It is F. Yeah, ma'am. Not using my.
Thank you all.
Thank you all. Thank you, sir.
Thank you. Thank you.